Thank you for that lovely introduction. I'm just wondering, up front, before beginning with my talk, why is everyone sitting on that side? Is there any particular reason for that? Okay, so thank you everyone for showing up to my talk and for your interest in mutation testing. I had the last time slot in Cape Town and the audience there was already a bit tired, so I want to make sure that you are awake now. So are you excited about mutation testing? A bit louder, are you excited about mutation testing? Great. Yeah. I don't want to waste too much time talking about myself. I'm Felix, I come from Germany as already introduced, and I work mostly with JavaScript and Python. You can check me out on Twitter with my handle there. And I want to start off with a poll. Do you enjoy writing software tests? Take away the impact of them, just writing tests itself. If you do, raise your hand. That's it. Do you like writing software tests? That's at least some, but still quite a minority. So like, to put this in perspective, in Cape Town only one person raised their hand. So yeah, because I know that for the most part I don't really like it, because I feel like it's both a very tedious and also boring task, especially writing unit tests, where you basically just copy-pasting the same assertions every time, every line, and then just changing the values. So for me, it's worth considering the question, why do we write software tests in the first place? So let's start with that. Although this question might seem a bit preposterous, it's worth thinking about. We write tests to ensure the functionality of a code base, to ensure that every line of code does what it is supposed to do, so that we have a well-working product. And we also write tests to find the hot areas in our code where errors accumulate and are likely to occur. And we also call them code hotspots. And ultimately, you need to write tests to stay at the top of the competition. In today's world, moving fast without breaking things is essential, and it is vital to stay at the forefront of the industry. So it is our duty as engineers, as designers, as product managers, to find the use cases for a product that will likely result in errors. And we are all responsible for finding the errors in a product so that we can fix them before the user detects them. But to fulfill the whole potential of tests and to maximize the effectiveness and usage of tests, and thus to minimize all workload on detecting and fixing bugs, we have to write good tests, which immediately raises the question, how to measure good tests? How do we determine the quality of tests? How do we distinguish the good tests from the bad tests? There are generally three approaches to measuring tests. First, you can ask how much of the software does the test suite cover. Second, you can ask how many use cases are covered in your test suite. And the third approach is looking at the different ways of testing. So do you have both, do you have unit tests, integration tests, end-to-end tests, and there are also more varieties. And all these different approaches should handle different responsibilities. The by far most widespread, and unfortunately sometimes even the only method of these three used to measure tests is code coverage. It measures the number of lines of code that are executed during the execution of the test suite. So you will then get a percentage of the code of your whole of your whole code base that is executed when you run your test suite. With the most code coverage tools, you will then get a table-like coverage like that, coverage report like that, with respective coverages for all parts of your app. Ideally, high code coverage implies code that is more maintainable and more readable. However, it is possible to achieve high percentages without improving maintainability, so to say, for the sake of coverage. In that case, you will end up in the danger zone down here. And in reality, this is not just any possibility, it is arguably happening at our everyday workspaces, where due to tight deadlines and strict goals, we content ourselves with a certain code coverage mark, instead of really considering what is my test worth. And that's the dichotomy of code coverage, quantity versus quality. Reaching 100% code coverage is easy, but does it say anything about the quality of your tests? Isn't pushing for the 100% code coverage just a compulsive obsession? Because does 100% code coverage really make your code base safer than 85% code coverage? No, not really. Just adding more tests doesn't make your test suite stronger. As with all other measurements, you get what you measure, and that's a thing that we all have to realize. And thus, we can conclude that code coverage is not the best indicator for test strength or thoroughness, which raises a question, what is the best indicator for test strength? This leads us to the single most important message of this talk, really. We are in need of an effective measurement of our test quality. After all, what's the point of testing if our tests don't cover all use cases? Tests are supposed to notify you of the possible routes for errors up front before you enroll your product to the user, to prevent you from delivering a flawed product to your customer. If you have to rely on your users to report their failing use cases and thus errors to you, you are not only losing your customers, you might also be wasting your resources. So anti-mutation testing, a long existing testing method that is now being revived. I will guide you through the what, how, and why of mutation testing. So without further ado, we'll just start with the first one. In short, mutation testing is a way to measure the strength of your test suite. Or in other words, instead of killing red error lines in your code, you want to kill mutants. Brief 101 on the steps of mutation testing. So step 1, you infiltrate a mutant, a virus, you could say. Like already mentioned, everyone likes mutants. No, we don't. But that's the whole point of it. This mutant is a small change in the program, so I've marked it black there. Like flipping an operator or just changing an absolute value. So for example, if you set a value in your code to 15, the mutant will be setting it to 16. So just a really small change in your code base. Your infected code with the mutant is now put in container. And then this container gets run through your test suite. So you execute your test suite on the mutated code, which we can also refer to as white box testing. So for those of you who are a bit into testing, you might know what white box testing is. It's basically taking the code, and in this case, it's basically taking the mutated code and running the test through it. So now that you have run your test and with the modified code, you can take a look at the test results. Let's say a particular test case has passed with your original code, and now with the mutated code, the same test fails. Now comes a revelation that might be a bit twisted. Your test failing is a good thing. It shows that the test that you wrote was good enough to detect that mutation. In other words, the mutant gets killed. On the other hand, if your test still passes, although there is like this modified change in it, the mutant stays alive. Thus, you've got to worry about your test cases and probably update them, because your test still passing means that if you once indeed have this flaw in your code, you won't notice it because your test won't indicate that you have this flaw in your code. Most of the mutation testing tools run these steps in parallel, so they will simultaneously generate multiple mutants. Each of them modifies a different small part of your code, and then the tool will rerun your test with each of them and compare the results, the test results before the mutation and after the mutation. Based on whether your tests still pass or fail after the mutation, or in other words, whether the mutant stays alive or not, we can now evaluate the effectiveness of our test suite. And if you remember, wasn't this exactly what we searched for? An approach, a tool to measure the quality of our tests. And indeed, using mutation testing, we can assess the quality of the test cases, which should be robust enough to fail mutant code. Mutation testing was originally authored by this handsome guy here, Richard Lipton, who is an American computer scientist and professor. Back then, the front-runner computers looked something like this in 1971, and they could barely handle large calculations. So although other scientists picked this method up and developed it further, it was just too resource-consuming and too costly at that time to do mutation testing properly. But today, we have access to unprecedented computing power, and hence, mutation testing has been emerging as one of the best ways to measure test suite quality. Going from the intangible to the tangible, let's take a look at a particular case of mutation testing. So, oh, what happened there? We have a method to check whether a user has a permission to view a document. Quite easy. Of course, also got a version for the Java reference here. So just a side question. Who of you develops in Java? Okay, and JavaScript? And the rest, 3, 2, 1? Come on, guys. A bit louder. C#, okay, all right. Yeah, unfortunately, I don't have anything for the C# friends, but C# is basically like Java twisted anyway, so. So we're gonna proceed with the Java version here. We write a test case for it, in which we want to ensure that a user with permission 1 can't view the document. So we pass in a user, and let's say the constructor that just sets the permission level. So we pass in the user with permission level 1, and the method should return false. Now let's apply mutation testing here. In this case, we've got several kinds of mutants. I've listed some of them here. The first 2 of which are called statement mutations, because the first 2 mutants directly take away what's behind the return statement and just replace it by, in one case, true, and in the other case, false. And the 2 mutants at the bottom are called relational operator mutants. Maybe you can already guess why, because they flip the relational operator, so the comparison that read there. So in the one case, they remove the equals, and in the other case, the mutant flips it to lesser than. Let's see how our test case works out. So we throw in the first mutant, return true, and if we run the test, it will fail now. That's great, because that means that we killed the mutant. Moving on to the second, this time the test passes. That means our mutant survives. So we've got to be cautious here. Let's do the other ones as well. For mutant 3, the test still passes, so the mutant still stays alive. So we can already see that our test case isn't any good. And mutant 4, where we flipped it, where the mutant flipped the comparison to lesser than, dies. And so the mutant dies. So to conclude this, we now know that 2 of the mutants survived, mutant 2 and mutant 3. This would equal a mutation testing score of 50%, which is atrocious. And this would indicate that our tests are of very poor quality. So we want to fix that. Let's kill the second mutant first. So to kill the second mutant, we have to add an assertion to check whether the method returns true. So let's quickly do that. So for example, permission level 3 should return true. And with that test case there, we have killed the second mutant. And we can also kill the third mutant, because the third mutant just removes the equals, and we can kill that when we introduce the test, an assertion that tests for permission level 2. And that's basically how mutation testing works. Quite simple, right? And now we've got like a perfect test case that covers all scenarios for this method. And admittedly, those 3 scenarios for this method aren't difficult at all to discover. But you will rarely face methods that easy and that simple in your daily workflow. And in those cases, mutation testing can be a huge help to discover the scenarios you didn't check in the test suite. In the previous example, we have manually created 4 mutants, but the mutation testing tools automatically generate mutants. And since mutants are at the very core of this whole concept, we want to take a closer look at them. By this point, you should already be able to guess the purpose of mutants, which is to simulate human programming errors. There are generally 3 types of mutants. 1, those that mutate a value. 2, those that mutate an operator, and 3, those that mutate a statement. Value mutations are pretty straightforward, so I've already mentioned that before, for example, just changing an absolute value. And statement mutations, we have already seen one example before, but the statement mutations are basically everything like duplicating a line of code, deleting a line of code, or changing a return value. And statement mutations are actually some of the most helpful mutations because we developers make a living out of copy-pasting code, we all know that. And these statements simulate this copy-paste behavior and likely issues that we face there when we forget to delete an unnecessary line, for example. There are also various options for operator mutations. Among them are arithmetic, relational, and conditional. I think these 3 are all pretty straightforward. Relational and conditional are actually pretty much the same. It's just distinguished between like those relation operators that are in an if clause and those that are in while or for loops, for example. However, mutation testing is not a panacea. In particular, it's based on 2 hypotheses. So we already know that mutants simulate human programming errors. But the first hypothesis is that mutants simulate errors of competent programmers. This is called the competent programmer hypothesis, and I agree that the name is a bit stupid, but this hypothesis basically says that most software faults introduced by experienced programmers are due to tiny syntactical errors. So for example, just checking the age and then forgetting the equals operator. And this hypothesis also says that programmers only write false programs that are in the general neighborhood of the set of correct programs. So you could say that mutants simulate minor or small programming errors. And the second hypothesis is called the coupling effect. It says that simple mistakes, those simple mistakes that experienced programmers tend to do, that simple mistakes cascade and couple. And this basically means that if, although the errors that we are likely to make are just tiny syntactical errors, these errors are so sensitive and far-reaching that more complex errors emerge. And based on this hypothesis, we can assume that every minor infection will lead to propagation, and thus we can, in theory, not only simulate the small errors, but all possible errors in a code base. And thus we can calculate a metric for the test suite covering the whole code base, which is just the number of mutants killed divided by the total amount of mutants. So that was a lot of theory. Now that we both know what mutation is and how the concept behind it works, as well as understand the functionality of mutants, we can jump into a live demonstration. So let me quickly switch to display. Mirror. And so right now the JavaScript friends can be happy because I've prepared because we are going to start off with JavaScript. So I've got an utilities file here, which basically just stores a bunch of utility functions, for example, as positive, absolute add, greatest common divisor, and functions to check whether a number is a prime or a string is a palindrome. So pretty simple. And I've also already written some tests for it, and you can already see that those tests are pretty bad. So we want to try to make this test suite perfect using mutation testing and find out all the use cases that we haven't covered yet. So we can run a mutation testing tool. This tool is called Striker. It's the most common mutation testing tool for JavaScript. And then we can just take a look at the report, and then I will guide you through this. So this takes a couple of seconds. So now we can go into the browser and have a fancy looking report here. So this is how the report, what the report looks like. We up here we have a mutation score. We now see that 82.2% of the mutants survived. So 8 of the 45 total mutants survived. So that also means that we've got a lot of test cases not covered yet. So we want to go through these. So let's just start with the first. So here we can see that the first mutant that survived was a Boolean substitution. So basically this mutant changed the false value to a true value. This is, as you should know now, a value mutation. So, where's, here. So does anyone have a guess how to kill this mutant? So this mutant survived when it basically turned this to true, and then it ran this test case here, and it still passed. So does anyone have a suggestion how to kill this mutant? Yes, correct. We have to do a contra test. Quite easy. So, for example, -1 shouldn't be positive. And then there are also two mutants that survived here. We can actually ignore the second mutant here because this is basically the same one as before. So with that test case, we've killed both mutant number 1 and mutant number 2. But we've got to take into consideration the mutant number 5 that also survived. And this survived, this mutant was basically just taking away the equals operator here. And this means that we can kill this mutant by adding a check for 0, which should also be true. So if you want, let me, can I somehow, yeah, open this up in parallel. So we're up here. So now we should have killed all mutants for the first function. So let's move on to this one. Here we have a binary expression, so an arithmetic mutant that survived. It changed this plus here. If we go in here, it changed this plus to a minus. So do you have any suggestions how to kill this mutant? Come on, guys. You are already programming for years. This is like things that you asked in high school. Should be as easy as just adding a number that is not 0. And then we can see that the GCD function is fine because there's no mutant that survived here, and we can move on to the isPrime function. So apparently we've got to fix a lot of test cases here. So right here we have, in this if clause, we directly have 2 mutants that survived. The first mutant is basically just changing the if clause to false, so that it's false in any case. And the second one was taking away this equals operator here. So we can kill these 2 mutants. So we can kill the first mutant when we add a test case that should return false for the number 1, and we can also add a test case that should return false for the number 0, for example, or any number that is lesser than 1. So let's do that right here. So 1 shouldn't be a prime, and 0 shouldn't be a prime as well. And then we can take a look at this Boolean substitution here. So this is, you can already see that a lot of the mutants are basically doing like equivalent things, and that we can, in some cases, kill multiple mutants with adding 1 test case. So we can move on to mutant number 22, which removes the equals here as well. So this means that when we have a prime that that's that can only be divided by its square root. So for example, 169, which can only be divided by 13, and 13 is a prime itself. This function should fail, but in this case, the test still passes because we don't have a test case to test for 169 or any other number that is only that can only be divided by its square root. So we want to add a test for 169, for example, as well. And now we can rerun this. And in a few seconds, take a look at how many mutants we've killed. Actually, we killed all of them. That's great. So that was a pretty easy. Pretty easy right here because the functions were pretty trivial. But I think you get the basic concept. And what's interesting here is that Striker is a rather new tool, and it's also developed across languages. So there's Striker for JavaScript and for .NET and also for Scala, I think. But what's quite interesting is that Striker, if we take a look at its website, here, only covers this amount of mutants. And then if we switch to the most common mutation testing tool in Java, which is PyTest, it has way more mutants. So if we now simulate the same function in Java, which is right here, let me enlarge that. And then we also have the test case here, split vertically. So these are basically just the tests that we've already that we've just discovered and just written in JavaScript. In JavaScript, it told us that this test cases were perfect and that we have mutation score of 100%. So now we want to run that in PyTest, so the Java mutation testing tool. And you will see that with the same test, actually, in Java, there is still one mutant that survives. So we want to kill that as well. So here you can see that the mutant that survived was a negated conditional. And now in this case, you can see that there are two negated conditionals here. This is because we have two conditions here. The first one is whether the first char is equal to last char, and the second one is whether it is a palindrome. So the mutant that survived negated this condition here. So the mutant that survived basically put in this, and the test case still passed. Which means, if you take a look at the code and what we are doing here, that we have to add an assertion with a word that where the first char equals the last char, but the characters in between don't make up a palindrome. So we want to add that. Assert false, for example, a devconf a. And now we can run that again. And we've killed all of them. So you can actually see that there was, in this case, that there is a difference between the tools. So you might want to take a look at the different mutants that all these tools have. And we saw in this case that there was actually one mutant that Striker didn't discover, but PyTest discovered. So we want to move on in PyTest. And I've prepared another class here, a stock service. So basically just a class to mock a stock of products. So we can initiate it with a default quantity, and then we can add stuff to the stock or remove stuff from the stock. So we've got an empty test here, and now we want to write the test for those together. So does anyone have a suggestion for, let me open this here. Actually, let's do it like that. So, does anyone have a suggestion for the first assertion? For, let's say, let's test add first. Anyone? Yeah, for example. So let's do that. Assert equals, if we add 1, it should be 101. So object dot add 1. Any other suggestions? Yeah. If we add 0, it should still be 101. And other suggestions? Yeah. What should happen if we check for -1? Yeah, illegal argument exception. So let's check for that as well. So it throws at -1. So, any other suggestions for the add test case, or do you think that we finished here? What do you mean?
So, for example, if the mutant fixed returns 101, then you're obviously going to come back to 101. But
Yeah. I think you've got to speak up a bit louder.
okay, so currently, if a mutant hardcodes the return value of add to 101, you'll always get 101 and both tests will pass. So you need to fix that. We need a different number other than adding 1 or 0.
Okay, so then what's your suggestion?
Add 5.
Okay, very creative. Okay, but do you think that we've finished the add test case right here? Okay, so let's move on to the remove test case. Any suggestions here?
Sorry, for the add as well, maybe assert that 0 doesn't throw an exception?
Yeah.
No, the inverse.
Hmm?
The inverse. So check that 0 doesn't throw an exception.
Yeah, we've checked that because we assert that if we add 0, it's still a 101 and not returning an exception. So, any suggestions for the first assertion in test remove? Yeah, if I add 5 to 101, it's 106. It's the same object, so it's static. Yeah, so I just heard that we want to remove 1, so let's just do that. It should be 99 after we remove 1. And then other suggestions? Hmm? Yeah, we can remove 0 as well. So so when we check for 0, we want to ensure that the mutant gets killed when it changes this to equals. Remove 0. And other suggestions? Yeah, we can do that, for example, as well. What should happen if we remove more than 100? Yes. Third throws if we remove more than 100. Or actually more than 99. Remove 100. So that should throw an exception. And I also saw a hand right there. Oh, that was the same. Okay.
There's another test case that you're missing, and that is that we haven't tested the initializer.
Mm-hmm.
So we need to test an initializer with another quantity other than 100.
Mm-hmm.
And
Okay, we can do that, but I'm pretty sure this is a bit redundant.
Testing the constructor, whereas we haven't checked for any mutants in the constructor yet.
Oh, right, yeah. Yeah, but... Yes, so we can, for example, do that here. A third throws class, remove -1. So now we have written a bunch of test cases, assertions here, and now we... Oh, right, yeah, it's this one, yeah. Yeah, this actually doesn't matter. So now we can check how well we did if we run the mutation tests. Actually, for this we can enable all mutants, which will take a bit longer, but it is. Because there's like a default class and an all class group of mutants, so we now enabled all mutants. So let's run that again. And let's wait till this is finished building. And oh, we see that we've missed one case. We've missed that if we remove a negative, didn't we check that? I think we checked that. Remove -1. This should be, oh no, it's changed conditional boundary. If we,
So if you remove 99 at the top one, it shouldn't work.
oh right, yeah, that's correct. Thank you. So if we remove 99, it should just be 0, right? So let's check that again. You're already doing well better than Cape Town. Yeah, that's great. So we saw that in this case, we managed to come up with like 99% of the scenarios, although we missed one. But you now should get the basic concept of mutation testing, and although these were like pretty simple examples, I think we can all agree that there are, for more complex apps, there are just dozens of scenarios that we don't come up with in our minds. So that's great that we finished this. Now we can switch back. Yeah. So I hope that this amazed you as much as it amazed me the first time I saw it. I think that it's pretty helpful. And if you aren't convinced yet, I do understand you, because maybe you're wondering, isn't this like extremely time-consuming? And we've already seen that even for this small app, it took like 10 seconds. And you would be totally right, because mutation testing is very time-consuming, and at the first glance, this time consumption stems from the huge amount of mutant programs that just has to be generated. And there's also another big problem that we call equivalent mutants. See, a mutation change is a syntactic change, but not every syntactic change also implies a semantic change. If a mutated program behaves exactly like the original program, there is no test case that could kill this mutant. So for equivalent mutants, there is no test case that could kill this mutant. And this is a big problem. For example, let's say you write a function that finds the maximal value in an array. Now with this mutant, right here, the loop starts from 0 instead of 1. This mutant is equivalent because it only adds an additional comparison of the first element to itself. This cannot change the behavior of the function. There's also another equivalent mutant here. The value stays the same, no matter whether the comparison includes an equals or not, because it will just change the same value. So you can already see that even for this very small function, there are already 2 equivalent mutants. So mutation testing does have some issues, but, well, every tool has its issues, right? And for the case of mutation testing, there are scientifically proven ways to optimize both speed and the detection of equivalent mutants. So, for example, there are mutation testing tools that mutate the bytecode instead of your programming language, which is a lot faster. Also, it would be more intelligent to just selectively run mutation testing, not on the whole code base, but only on the small parts that you've just changed. So there are ways to optimize that. And taking into consideration that mutation testing is being revived as a rather new approach, because people are realizing that we do need some metric for test quality. So if you manage to jump on the train before it becomes a bandwagon, you will have a significant advantage. And I've been using Striker, so the JavaScript tool, for some of my personal projects as well, so mostly websites. And I've never faced major performance problems, because if you do mutation testing selectively, as I already said, it doesn't take too long. And as I already said, this is not a panacea. You're probably going to use it alongside other tools anyways. So if you mutate intelligently, you're good to go. Therefore, we can conclude that mutation testing is a powerful approach to attain both high code coverage and maintainability of the source program. And we can thus get out of the danger zone all the way up there to an ideal test suite that both covers the whole code base as well as features high-quality tests that simulate all possible use cases. It allows us to find the ambiguities in your code and detect routes for possible software errors that we wouldn't have come up with ourselves. And also you can integrate it into your existing CI tools, although you shouldn't let it run on every commit for obvious reasons, and especially on the whole code base, as we've already covered. And as we are approaching the end of this talk, we rewind to the start of our talk where we talked about code coverage. Here you see a plot from a study paper by a professor from the University of Helsinki. In his study, he compared dozens of CS students' test suits code coverage percentage with their mutation score. And he found out that engineers can get rewarded for high code coverage, although their tests are of very poor quality. So the most obvious example is this right there. I hope that none of your code bases would land anywhere there. But you can see that having a high mutation testing score almost always correlates with a high code coverage score. So all the test suits that have a mutation score of 80% or higher also have a code coverage score of roughly 90% or higher, while the opposite cannot be said. So for example, we have a couple of test suits that have a high code coverage but a very poor mutation testing score. Some decades ago, people believed that testing their programs was too overkill. Today, we have realized that testing is necessary and that it's very useful. I believe it's time to move on and try out something new that facilitates our test suites to a new level. So, my name is Felix. If you enjoyed this talk, please follow me on Twitter, and thank you. And please stay here. I wanted to take a selfie with you. So
Okay, everyone smile.
Everyone smile. Pretty cool. All right, thanks.
Felix. That was excellent. So we have 5 minutes left before the movement session starts. Any questions or contributions you want to make from the floor? Let me give you the mic so that you are heard on the video.
I just wanted to ask, for C#, would you recommend Striker.net, or is there another library you're aware of for mutation testing for C#?
The only one that I haven't searched for it. I just stumbled upon Striker for C#. You might have to look it up yourself, but I know that Striker runs pretty well. And also for .NET, they have a couple of other mutants as well. So, yeah.
I've got a
a couple of questions. So the first one is, is there a particular approach that these tools use to decide which mutants to apply? So I'm particularly asking from a point of stability. So for example, you've made a change to your code. How does it make sure that you have a repeatable test, or is that not important? Or are you going to get different results every time you run the test, basically?
No, you get the same results every time. So if I understand your question correctly, you're asking how the tests, how the tools select the mutators.
Yes.
So I haven't dig too deep into this, but from what I've seen in the code base as well is that they analyze your code and they basically search for those absolute values, those relations, those return statements that they can mutate, and then they just apply them. So I can also show you that there are. So PyTest, for example, has fixed mutation operations here. So for example, you can see that once it finds this operator lesser than, it will change it to a lesser equals.
All right. We can't quite
red.
see it. But
Oh. Sorry. Let me move that over. Yeah. So
all right.
once it finds this, for example, it will change it to this.
Okay, and then the next question is, similar to the idea of chasing 100% code coverage is a bit silly. Is there like a sweet spot in terms of should we be chasing 100% resistance against mutations in our tests, or is there sort of some kind of data on how mutation resistance correlates to maintainability or other code qualities?
So there are some research papers on this indeed, and so the plot that I showed is from one of those. And there is actually a correlation between there was one research where a professor let the students write test suits, and then they gave them to other students to try the programs out, whether they found it very good to use or whether they found any errors. And there was a correlation between product quality and code and mutation score. Yeah.
Excellent. Thanks so much.